All right, so welcome to week 6 of machine learning for healthcare. A slight change of plan. So initially, the syllabus said that we'll be studying concept embedding first and then interpretability. But I actually put interpretability first, and then we'll take a look at the concept embedding because domain knowledge embedding is actually quite closely related to concept embedding. So I thought it would be a good idea to actually look at this first and then look at concept embedding next, because concept embedding might not be completely. I mean, yeah, it has more concern with domain knowledge embedding rather than interpretability. But it's like it sits in between. So yeah, I just uploaded the slides for interpretability on Classroom. So please download it if you want to. 제가 그 인터프리터블 요 슬라이드를 지금 막 클래스룸에 올렸으니까 필요하신 분들은 지금 다운 받아 주세요. And so this is the first week after the project week, so hopefully everybody is doing their projects okay. So any question regarding the projects? Maybe I'll just answer 1 or 2 questions. So and then we'll just move on with the material. 혹시 그 프로젝트 하시면서 뭐 궁금하신 거나 뭐 피드백이나 이런 거 있으신가요? 이제 저번처럼 뭐 계속 받아줄 순 없고요. 혹시 궁금하신 거나 뭐 이런 거 있으면 제가 짧게 한번 답변을 드리겠습니다. 네네, 질문하세요. Okay, so before Hyunji was able to ask first, so I'll just answer Soro first. So if the file size is too high, can we submit by email? How large are the files? Because I think the limit is 1 gigabyte, which is pretty big. Soro, so how large is the file? Less than that. Okay, so if it's less than 1 gigabyte, maybe it's easier to, because if people start sending their submissions via email, then it'll be hard for the TA to actually collect them and then evaluate them with the scripts. So hopefully everybody can just submit on KLMS. And 그리고 네, 현진님 질문은 교수님 수업 시간과 질의 응시 서미션의 어디션 DX를 열다가 요거는 그 어드미션스 테이블에 가보시면 다이그노시스라고, 다이그노시스 맞나요? 잠깐만, 저도 지금 찾아보고 있습니다. 네, 어드미션스에 가면은 다이그노시스라는 항목이 있는데요. 그 항목이 아니라 이제 컬럼이죠. 이게 관계 DB니까. 어드미션스 테이블이 피처가 아니라 컬럼 다이그노시스가 이제 스트링으로 저장이 되거든요. 근데 그 종류가 제 기억이 맞다면 14개 정도의 14개가 넘을 수도 있고요. 네, 뭐 정확하게 몇 개인지 모르겠습니다. 하여튼 간에 뭐 몇십 개, 몇만 개 수준은 아니고 몇십 개에서 몇백 개 수준의 이 병명이 있어요. 근데 병명이 아니라 실제로 이제 여기에 병원에 입원을 하게 된 이유입니다. 네네. 그럼 14개가 아니었나 보네. 제가 착각했나 봅니다. 네. 근데 그게 그 ICD-9 테이블스의 그 ICD-9만큼 막 만 몇천 개 이렇진 않습니다. 네. 네, 그리고 성진님, date of birth 기준으로 ICU 입원 당시 나이를 계산했는데 영살 또는 300살이 발견되었는데요. 가상 데이터인이 의도한 걸로 생각하고 써도 궁금합니다. 영살은 실제로 영살이에요. 왜냐면 태어나자마자 바로 ICU에 들어갈 수도 있기 때문에 이제 뭐 그냥 신생아인데 이제 뭐 문제가 있어가지고 들어갈 수도 있죠. 그래서 뭐 그런 경우도 있고 300살인 거는 그 제가 이제 예전에 수업 시간에 말씀드렸는데 이 프라이버시 그러니까 이제 개인정보 보호를 위해서는 특정 정보를 가려야 되거든요. 예를 들어서 이제 내가 뭐 생년월일이랑 주민번호랑 이름만 지운다고 되는 게 아니라 그때 말씀드렸듯이 너무 희귀한 질병이 걸려 있거나 이러면은 그 이름이나 생년월일 지워도 그 병 걸린 사람이 뻔히 누군지 알기 때문에 이게 의미가 없잖아요. 그런 것처럼 나이가 예를 들어서 뭐 100살이 넘는다, 또는 90살이 넘는다 이러면은 또 너무 초고령자래 가지고 그런 사람이 미국에 뭐 몇 명 없을 거 아니에요. 그렇기 때문에 이제 그런 분들 전부 다 300살로 퉁쳤을 거예요. 제 기억이 맞으면은. 그러니까 이제 몇 살 이상으로 너무 초고령자여서 어느 정도 특정이 가능하다, 리아이덴티파이가 가능하다 그러면은 아마 전부 다 300살로 그냥 다 묶어버렸을 겁니다. 그래서 그때는 이제 나이를 피처로 쓰지 않는 게 좋겠죠. 네. 혹시 답이 되셨나요? 네네. Oh, okay, so that was an interesting question from Songjin Park. The question was that based on the date of birth and the time at the time at the admission to the ICU, some patients were 0 years of age and some patients were 300 years of age. So the former case, which the 0 years of age, 0-year-old patients, that is totally okay because some patients are actually neonates. So neonates being like newborn babies. So newborn babies might have some severe problems. So they just, as soon as they were born, they're transferred to the ICU. So that's okay. But the 300-year-olds, that's a special case. So if you remember, at the first or second class, I briefly talked about the privacy issues and the HIPAA law. The HIPAA law is the guideline. Actually, it's a set of rules that must be met for the EHR data to be anonymized before being open source. So one of the rules is that people who are like really old, like really old, like 95 years of age, or maybe like 100 years old or 120 years old. So those people, even without their names and their addresses, their social security numbers, all removed, you can still kind of re-identify who they are because there are only so many people, like very small number of people in the United States who are, for example, like 120 years old. So in that case, all those people are just grouped to the age of 300. So anybody who is 300 years of age in the MIMIC dataset, it means that they are just really old. So maybe like I forgot the exact number, I forgot like whether it was maybe 95 or 90 or 85. Like if somebody is at least if is greater or equal to the age of like say 95, then they are just all mapped to 300. So that so there's like no chance of re-identification. So that's why you see 300-year-old patients. Yeah, that was an interesting question. Thanks. All right, so before we move on to the material, any last question? Hopefully everybody is having an okay time with the project because it's a relatively easy project, and if you just put enough amount of time, you can hopefully everybody can do it. All right, so if there are no more questions, we'll move on to the interpretability. All right, cool. Where's my slide? Okay. All right, so the predictive, so what we've learned so far for the first 4 weeks was predictive models. So predictive models are probably the most basic stuff that a lot of people actually try when they want to do something for healthcare using the AI technology or specifically machine learning. So usually it's trying to predict like a disease or diagnose a disease. So prediction and diagnosis is actually kind of slightly different. So diagnosing a disease is like, you know that there's something wrong with the patient. So you want to find out what specific disease the patient has. So that's diagnosis. Like if you watched Dr. House, House, 그 드라마 보신 분들 아시겠지만, so in that drama, the main characters, they do like something called cross diagnosis or something like X diagnosis. So that is what they do when they will know that there's something wrong with the patient, but they don't know exactly why the patient is ill. So they try to narrow down the list, the candidates, the list of possible diagnoses, and then they come up with one or two, like, concrete diagnosis, so that they can start treating the patient. Like if you don't know what's wrong with the patient, then you can't treat them. So that's what diagnosis is. And prediction is actually a bit different. Predicting is something you do for the future. So the patient is not ill yet, but maybe within a year or two, or maybe like, maybe next month, something like that. Like in some future time frame, you're trying to predict what would happen to the patient, medically. Like some maybe the patient will have a symptom, or maybe will be ill, or maybe will die, or will be readmitted. Some medical event that should happen in the future. That's prediction. But both are actually can be thought of as classification. So if you are to use a model for those types of tests, like diagnosis or prediction, you would probably use a classification model, like a sigma, like you would put a sigmoid or softmax on top. So that's like, even those two models are, those two tasks are semantically different. Technically, you would be using the same model. And as I was saying, so you would be, a lot of people try with the either regression model, so predicting a scalar value, or classification model when trying to combine machine learning model techniques with healthcare problems. So that's why we took a lot of time, roughly 4 weeks. So that's about 8 sessions to learn from A to Z. So you have a data and you have a task, and then you can start doing the building predictive model, because we've looked at the tasks, and we've looked at the data processing, and we've looked at the model. So those 3 are like the pillars of predictive models. So if you have followed all those material, and if you understand all these topics, then you are actually good to go. So the rest of the class, rest of the course is actually just more or less application of these fundamental topics. So if you have any question regarding the predictive model part, you can please, ask as soon as possible. So after like the 7 or 8 weeks from now would be more focused on, we're not going to focus on the technical details, like pre-processing and stuff. Like those are now over. So to some of you, maybe that was the fun part. To the other some of you, maybe now it is the fun part. All right, and the project 1 was ICU mortality prediction, and so if you think about it, you are using all these things like task, data processing, modeling for you. When doing project 1, you would be using all those topics that you learned for the first 4 weeks. So ICU mortality prediction, that was the task part, and you needed to understand the spec, and then the processing was probably, that was like the 80% or 90% of the project. And then machine learning models, you just call them using scikit-learn and PyTorch. So that's actually the easy part. All right, hopefully that project was a helpful one. And today's focus, actually this week's focus, not today's focus, this week's focus is interpretability. We'll first look at the logistic regression versus neural network. So this is a linear model. So linear model versus non-linear model, that would be more accurate. And then there are 3, if in my opinion, as far as I'm concerned, there are mainly 3 techniques for making a model interpretable, or maybe trying to explain away what the model is doing. So one is gradient-based approach, and the other 2 are neural attention models. So attention models also often used to understand what the model is doing. And the third is model agnostic approach. So we'll just take a look at 2 well-known techniques for the last, Shapley value and line. And for the neural attention, we'll be looking at a model called Retain, which is actually a model that I proposed and was announced that was proposed in Europe's 2016, so which is a pretty well-known model for interpretable healthcare prediction. A gradient-based approach will not be actually looking at this too much, because you've probably looked at like a lot of people are already familiar with grad chems and chems and layer-wise relevance propagation and that kind of stuff. And those are usually heavily covered in the computer vision class, actually. So anyway, we'll start with the linear model versus nonlinear model. So interpretability, or some people call it explainability. Oh, actually, this is a typo. I'm sorry. Explainability. Explainability. So I would say those two are interchangeable terms. So what does it mean? What like if you want to say your model is interpretable, for example, you are a startup company, or if you're a team at an IT company and you want to sell your predictive model to a hospital, or maybe Shimpyeongwon or wherever, and you want to, and one of the features of your product, which is a predictive model, is interpretability. And how would you convince your buyer, your clients, for example, the hospital decision maker or Shimpyeongwon decision maker, how would you convince them that your model is interpretable? So what is the definition of interpretability, actually? So that is, I would say, it's still not really concretely defined, because people would like to claim their models are interpretable because it's such a nice word. And a lot of people call neural networks a black box model, and so it means it has a rather negative connotation. We don't understand what the model is doing, as opposed to logistic regression, which is a bit more easier to understand. So if you think that a black box model is a bad thing, then you want your model to be the opposite of that, which is interpretable model, for example. And if you were to, if you were to convince your buyer or your client that your model is interpretable, how would you do that? So because in order to do that, you need to define what interpretable is, and people have different definitions. So, and a lot of, I'm not sure about these. I'm not sure if like interpretability is still like a big issue these days, but maybe a couple years ago, it was a big issue. And there was I think it was an Apple paper, EMNLP paper, a paper named "Attention is Not Explanation." I think that was the name of the title. So that was like still up for debate, like whether attention is it corresponds to interpretable model. And then after that came another paper called "Attention is Not Explanation." So that was, it was a bit of a interesting topic back then. I think that was maybe a year or 2 years ago. Right, so interpretability. So as I was saying, interpretability is still not a really mathematically quantitatively defined term. And linear model versus nonlinear model. Why do we call neural networks a black box model? So we'll first look at the linear models, or logistic regression, to be concrete. So it's logistic regression model is a linear combination. It uses a linear combination of predictor variables, or the same, semantically the same features. So linear combination of features. So if you remember this diagram from maybe like three or 4 weeks ago, logistic regression is just a single neuron with a sigmoid function used as the activation function. So that's a logistic regression. So we're just looking at looking at the architecture again, and this is still the 40,000 patient representation, or actually this is admission representation vector, if you remember the material. And you would put one, each dimension corresponds to a single feature. So there are 3 types of admission types, like elective, emergency, and others. And there are 5 different types of marital status, like married, single, widowed, whatever, like separated, whatever. So each of them would correspond to a single feature, and then there would be a corresponding weight or coefficient, which is the W here. So there's a vector of weight vector, and each element of the weight vector corresponds to a coefficient for that specific feature, and then you add them up. So you do a weight sum of these two, the weights and the features, and then you have a single scalar value, and then you put them through a sigmoid function, and then that's how you get the output. So if you think about it, then what does it mean if a certain weight is positive or negative? So this is a very simple stuff. So for example, these 5 stuff, the marital status, 5 types of marital status: single, married, divorced, widowed, other. For example, if W3 has a positive value, for example, like 1.0 or 2.0 or maybe 10.0, what does that mean? Or if W4 has a negative value, what does that mean? So it's easy. So if W3, let's say that we are doing readmission prediction. So this represents a single hospital admission, and based on this, we're trying to predict whether the patient would return to the hospital within 30 days after discharge. So that's our task. And if for that task, you've trained your logistic regression model using maximum likelihood estimation with a gradient descent algorithm, and after that, you've found that your W3 has a positive value. If that's the case, then it means that being single has a positive correlation with your likelihood of being readmitted to the hospital within 30 days. So that's what W3 being positive means. Conversely, if your W4 is negative, then that means if you're married, then the likelihood of you being readmitted is lower. So there's a negative correlation between the two. So hopefully this is super easy for everyone. And that's as far as it goes. So it's a correlation. Whether it's positive correlation or negative correlation. And of course, if you are familiar with the statistics and all the confidence intervals and stuff, then you would start to estimate how accurate the W3 the value is. But we're not going to do that because this is more or less but that's not the focus of this class. So if you think about it, so this is one of the reasons why people call linear models, logistic regression. There are other linear models like support vector machines and that kind of stuff. But this is mainly the reason why people call logistic regression or linear models interpretable, because if you can take a look at the coefficients and then understand the correlation between that feature and the outcome. So, and the formula, the equation is also super simple. You just multiply your weight vector. You just simply multiply your weight to the individual features, and then you all sum them up, and then put it through a sigmoid function. Or if it's support vector machines, then it's something else. But anyway, so basically there's always a single weight vector and a single feature vector and a dot product between the two. And that's it. So it's easy to understand why you have a certain outcome, like a value between 0 and 1. But are linear models always interpretable? So that's also a question. So for example, if your logistic regression has 1 million, so you're using 1 million features for your logistic regression, and that is absolutely possible. So for example, if you are using, like if you're doing something with the NLP task, then your model can easily have a 1 million feature. For example, you can mix a unigram feature and bigram features and trigram features, and as you go on with the n-gram features, you would easily you can easily reach 1 million features. So that is For example, let's say that you're using bigram features only, and there are only 1,000 unique words in your data set. And if you do bigram feature, that means that you are taking a pair of words as a features. And a pair of words, of course, how many cases can there be? If there are 1,000 unique words, it would be 1 million. So 1 million features is not a crazy number in NLP. And you can, for example, if you do like document classification, whether or a sentiment classification, given a sentence or a document, you want to classify whether the given text is positive or negative. So in that case, you could use logistic regression. And if you use bigram features, you can easily have 1 million features for your logistic regression. And can you call that model interpretable? If it has 1 million features, it will be using 1 million dimensional feature vector with 1 million dimensional weight vector. And if you probably don't have enough time to understand which ones are more important and which ones are not, and why you got a vector, why you obtained a value of for example, like 0.8 or 0.1. Of course, you can rank the features by their absolute values. So if you can take a look at top 10 or top 20 most strongest weights or strongest features that have the largest weights, and then maybe just get a glimpse of what the model is doing. But that still is not a complete understand. You don't understand the complete picture, because there are so many features. And even if, for example, to make things worse, what if your weights are more or less uniform? So as I said, even if you have a lot of features, you can still rank them by their magnitude. But if your features are more or less the same weights, all of them, then what would happen? So like everything is like 0.01, 0.01, 0.01, like, or negative 0.01, 0.02, something like that. Like it's very, very minuscule difference between the feature strength. In that case, can you say that there are any insights? Like, can you say that there are any interesting insights that you can find from the model? Or like, can you call that model interpretable? You might be able to say that there is nothing to be interpreted for those kind of models where the features have uniform strength. Like, it's just nothing. If everything is useful, it means that nothing is useful. So there were some efforts to prevent that kind of non-interesting cases with very more like uniform distribution of the feature weights. So there are some regularization techniques to overcome this, such as L1 regularization or lasso regression, in other words, an elastic net, and maybe a bit more advanced group variable selection. So hopefully you've heard about these in your basic machine learning class. I forgot if it was like 501 or 502 or 503, but hopefully at least everybody understands what L1 regularization is. Are there anyone who don't know what L1 regularization is? If so, I can just briefly explain, but if not, I can just move on. All right, so I guess everybody understands about L1 regularization. Okay, so because of the characteristics of the L1 regularization, the features or the feature weights become sparse. So if you heavily regularize your logistic regression model with L1 term, using like a really big term for the big coefficient, the control variable for the L1 term, then most of your weights would be 0 or very small, and then only small percentage of your entire features would survive. So in that case, you would, of course, the assumption is that you would not be sacrificing too much accuracy, but in doing so, while you're doing so, you would be retaining only a small fraction of the entire features, and that makes the model more interpretable. elastic net is a combination of L1 and L2 regularization. So for example, you could start with L2 regularization, get the model, get the feature weights, obtain a relatively small feature weights because of the L2 regularization. And then after you've done that, you run one more time with L1 regularization to make them sparse. So that would, I mean, it's just a form of elastic net, but basically elastic net is a combination of L1 and L2 regularization. Group variable selection is a bit more involved. So you want to select a group. You want a group of variables to survive rather than individual, like every feature is on their own. Rather than that, you want a group of features to survive, and there could be like a lot of different groups. Yeah, but anyway, so those are all L1 organization, L1 elastic net group variable selection. They're all like you could see them as a type of techniques to obtain smaller number of active features when you have a lot of possible features, such as like 1 million features like here. So that's interpretability, the relationship between interpretability and linear model. Neural networks, on the other end, it's not so easy. So if you think about interpreting the weights W3 and W4, directly seeing them as a correlation between a feature and the outcome, you cannot probably do that with neural networks, because first of all, it has a nonlinear activation with multiple layers. So for example, what happens, what does it mean? So you can see that a single feature here is impacting all those 4 hidden neurons, and then all those hidden neurons are contributing towards the final outcome yn, or final outcome y. So in order to understand the impact of the first feature here, you would have to study at least like 8 weights. So for example, what does it mean if V11 is positive and W1 is positive? But then again, what does it mean when V12 is positive and W or like V1? I mean, for each pair, there could be 4 cases: V11 and W1 being both positive, V11 being positive and W1 being negative. So you would have to and then there are 4 features here. I mean, there are 4 neurons here. So you would have total, how many, 16 cases for a single feature here. So it's just and that's just when you have one single hidden layer with only 4 neurons. So if you think about multi-layer and a lot more hidden neurons, like 256 hidden neurons or 512 hidden neurons, you can it's just impossible to track down how individual features are impacting the final outcome. So there are some, that you could, if it's only a single hidden layer, there is a bit, you could think of it, you could make it a bit more interpretable by looking at high level features. For example, let's say that there are only 8 features, 8 input features for this specific model. And let's just say that this is still a readmission prediction model. And there are 4 hidden neurons, and there's only a single hidden layer. And let's suppose that these arrows, there are a lot of like black arrows here, but not all, it doesn't represent all possible arrows. So let's just assume that these arrows indicate non-zero weights. So for example, let me just annotate a little bit. For example, weight here and here and here. Like these weights are all zeroed out. For example, let's just assume for the sake of argument, let's say these features, and of course this one and this one, they're all zeroed out. So let's just assume that these are the ones that survive. So if you think about it, then the marital status 0, which was like the last marital status was other, and the last admission type was other. So the H1 represents a patient or an admission type, because this is a admission representation. So H1 represents the admission type where both admission type and marital status were 0, were other. So this represents other group. And for example, here, like let's say that H3 was, this was emergency. For example, this was like elective, walked in, and this was emergency, this was other, and this was single and married. So in this case, H3 represents patient groups or admission groups that were admitted via emergency room when the marital status being married. So H3 being that type. So there are roughly 4 types. So what this is doing is the high level. So this input feature, they are like low level features. They all like you have to look at all the individual features. Like there are 8 feature types. So you have to look at all the 8 feature types and try to understand what the patient is, but then what the patient's information is. But then in the high level or the hidden layer representation, the representation is a bit more. Actually, it is directly high level. So it is a bit more like aggregated. So this represents all the patients who are admitted via other means, and the marital status being other. Like this is all the patients who are married and were admitted via emergency room. So it's a bit more like an aggregated. So semantically, it's a high level meaning. And then based on these features, based on these groups, you can then do a weight. Based on these features, you are doing weight sum with the W vector and then deriving the final outcome. So in that case, once you figured out what individual like hidden neurons represent, then you can try to understand what W and try to see what the W1 vector, W1 weights are whether they're positive or negative. And for example, if W3 is negative, then it means that if you are married and if you've come to the hospital via emergency room, then you are less likely to be readmitted. That's what W3 means. So you can still do a lot more like. It's a bit tedious because you have to understand what each individual hidden neurons represent, but still it is not impossible to try to understand or interpret neural networks. But this is only like a single hidden layer with 4 neurons. So if your model looks like this, then there's no way you can understand what this model is, how this model is aggregating information into high level meanings. So yeah, it's virtually impossible. So so this kind of thing has a limitation. All right. So that is why we are going to talk about techniques to make your model interpretable, or techniques to interpret your models. So first is interpretability, mostly in computer vision using gradient-based methods. So unlike the next one, which is the attention-based models, unlike the next one, this model, this strategy or this method technique for this interpretability technique is not can be used on a already trained model. So it's like a post-processing. The attention models can be designed to make the model interpretable from scratch. So it is by nature interpretable, the attention models. But in computer vision, like GradCams and like the gradient-based methods and those kind of stuff, like looking at the filters and all that, those are not those are like post-processing methods, because the model was not built to be interpretable by nature. So it's like an afterthought. So there are various ways you can visualize the activation. So visualizing activation means you can look at a single hidden neuron, or like the outcome of the convolution after a single layer. You can look at the activations and try to understand what's going on. Or you can actually synthesize inputs that maximize the output. For example, like if you have like a dog class, like maybe like an ImageNet classifier, and you can actually try to once you've trained your model, so training is actually optimizing or estimating the weight vectors, the weights of your model. But once you've trained them, then you can actually do a backprop in terms of the input. So you can actually learn the inputs by backprop and trying to maximize a single output. So like if you have like a, if you think about the ImageNet classifier, there are 1,000 heads, 1,000 output heads, and you would be selecting a single head, for example, like a dog or a cat or a bicycle or like truck or car, whatever. You select one head, and then based on the head, you are trying to maximize that head's probability in terms of the input. So you can actually train them with gradient, like stochastic gradient descent, and then try to synthesize what kind of input would maximize the output head that you've just chosen, for example, a car. So you can do that. You can actually calculate class activation maps as well using cams and grad cams. So we'll just look at a couple of examples first, and then try to understand what it means to visualize your model using gradient-based methods. But we won't go into detail. We'll just look at a single paper. So, oh, sorry about this. All right, let me share the screen. All right, this is this is a paper titled Understanding Neural Networks Through Deep Visualization, which is a really old paper by today's standards. So it was presented in 2015, so about roughly 6 years ago, and it was from Cornell University. This is probably one of the very, very first papers that tried to understand what neural networks, specifically convnets, actually, to understand what the convnet is doing when trying to classify certain images. So if you look at the pictures here, we won't go into the details, but we'll look at the pictures mostly. So this is a what data set is it using? Let me see whether it's ImageNet or it doesn't say anywhere what kind of data set that they used. Let's go to the experiments first. I'm not really sure. I think probably it's ImageNet, because the model that they're using is like they're referring to a lot of ImageNet based architectures. So, for example, like VGG nets and that kind of stuff. So, oh yeah, here it is. Like it is state-of-the-art performance ImageNet benchmark on 2013. Xyloferg, I think that's VGG net maybe. Anyway, so they're looking at actually what the filters being the convnet filters. So, for example, for a dog, like certain filters, if you visualize the output, then it kind of looks like a dog face or a flower. So like if you look at here, kind of looks like a Yorkshire Terrier or something. And here, well, they claim that it's a human face, but I'm not sure if it looks like a human face. This definitely looks like, oh, I thought this looked like a wolf, but they say it's a cat face. Anyway, yeah, you can actually see. So these are like all different convnet outputs. So this is like conv 5 of the second layer or 151 layer. I'm not. Yeah. Oh, actually, I think that's like because you probably use a lot of filters per layer. So maybe this is like a fifth layer convnet and second convnet filter of the fifth layer. And this is like the 151st convnet of the fifth layer, something like that. So you can actually visualize the outputs, and there are a lot more. Yeah, here it is. So a lot more visualization examples. So like a lot of filters actually are well tuned towards looking at or detecting flamingos or pelicans or hartebeest. I'm not sure what hartebeest is. billiard table, also doing a very nice job. This is actually, it does look like a billiard table. So 당구대 같죠. Then types of insects, cobra, a snake, station wagon. So it's a car, and a black swan. So I'm not sure why exactly they call it a black swan. And yeah. So yeah, yeah, you can see a lot of what the filters are doing. So, and even for like a single same layer, like they are focusing on different stuff. And because it's there are 1,000 classes to classify, because it's an image, supposing that this is an image and classifier, then the filter has to do a lot of jobs to figure out different types of classes. So that's why you see a lot of different, different like entities or different classes being activated by certain features, certain content filters. So this was the very first effort. I'm not sure if this was the very first, but this was like one of the very early efforts to understand what the model was doing, especially confidence. So, and yep, depending on the layer, especially depending on the layer, it's a very interesting concept, because I'm pretty sure a lot of you are already familiar with the concept of confident being inspired by how human visual cortex functions. For example, like the lower visual cortex, like the first thing that we see is like the very simple patterns, like textures or like edges, and then we mix and match them up to understand like local shapes, and then we again mix and match them up to understand a larger shape or larger features, and then finally we see like a human face or like a cat face or something. So that's what roughly how the human cortex is working. And similarly, if you look at confident filters of a multi-layered confident, it looks a bit similar. It works a bit similar to how human visual cortex works. So the layer one, the very first layer, these filters are, so I'm not sure why they made it so small. These filters are focusing on very simple patterns, like diagonal patterns, or like black and white horizontally, something like that. Like different colors, because colors are like not just edges and texture, but the colors are also important information. So very simple patterns with very simple colors. And then if you go to layer number 2, you start mix and matching. So for example, like you just seen with the marriage status and the admission type, mix and matching to the different hidden neurons, you start mix and matching these different filters to get a bit more high level concepts. So these features here are a bit more complex than the first layer features, but still it's not really recognizable. I think it kind of looks like a fur or something. And if you go to layer number 3, that's when you start seeing like this kind of look. So this is layer 3. So layer 3, you start seeing like human-like shape here. Others, I'm not so sure. Yeah, I'm not really sure. So in layer 4, now you see a spherical shape or like a circular shape. This looks like, so this was like the dog-like thing here. Looks like, I don't know, like an owl or bird. And then if you go to layer 5, layer 6, like the filters become more complex, and it tries to capture a bit more like high level features. Like you start seeing like dog faces here and like spontaneous stuff. And then if you go to layer 7, layer 8, now by layer 8, you start seeing like concrete objects like ships here, chairs, teddy bears, a tie. It's specifically a Windsor tie, and a pitcher or like a teapot or something like that. So the model is starting from the very simple stuff, like starting from mere patterns here. It is learning to mix and match, basically combine those simple features in a repeatedly complex manner to arrive at this really complex object detection filters, which is pretty amazing. So back in like 2015, this was like a very it was a very high impact paper. Yeah, and yeah. I mean, a lot more patterns. So if you're interested, you can download you can visit this website, or actually you can read these papers by yourself, because I put the links there in the slides, so you can click them. All right, so basically, so these are trying to visualize with the gradient-based methods. So we won't go into the details. Probably a lot of you already took the computer vision class, like, last year, or maybe this semester. So maybe one of the class topics would be visualizing the convolute inputs or convolute filters. All right, back to the slides then. Can anybody actually, so anybody who actually attended the computer vision class like last semester, were there any like components or topics related to interpretability or grad chems, that kind of stuff? 혹시 수업 들으신 분 그래드캠이나 뭐 저런 뭐 옵티마이제이션 기반의 그 비주얼라이제이션 같은 토픽 같은 걸 다뤘었나요? 컴퓨터 비전 수업에서? 컴퓨터 비전 수업 들으신 분 없나요? 아니면 이번 학기에라도. Okay, we have not reached that chapter, but there is a chapter dedicated for interpretability. Is there? Not sure. Sorry. Okay, not sure. I guess maybe not. Maybe interpretability is not part of computer vision class, because computer vision is such a vast, comprehensive, like it's such a vast topic. Like, generating images or like that alone can take up an entire semester. So I guess interpretability is not as high priority as I would think, but if you're interested, you could take a look at. There is also a reference here that I've prepared. It's I think it's a personal website from some guy, maybe not a guy, some researcher or some student. I'm not really sure, but it has a laid out the like overview of gradient-based visualization methods or gradient-based interpretability methods overall. So hopefully, there is a chapter on visualization. Okay, yeah, cool. Yeah, as I was saying, if you're interested in the overview of the gradient-based interpretability methods, you can visit this website. All right, so we're gonna move on to the neural intentions now. So anybody who's taken the programming for AI class last semester, you're probably familiar with the attentions. If not, maybe NLP, NLP class will be teaching now attentions, obviously. So I'm just gonna skip through the details. Hopefully, I'm assuming that everybody knows what attentions is. But if you are not familiar, just let me know, and then I can slow down and focus on parts that you are not familiar with. But yeah, I'll just go on, assuming that you are all familiar with the attentions. So attentions was proposed by Baranao, Cho, Benjo in iClear 2015. So it was proposed to actually improve the performance of neural machine translation and NMT. So it was not used for interpretability purposes, but it was more or less used for improving the accuracy of the translation model. But it had a lot of really good side effects. So it's no longer a side effect, like a good benefit, such as interpretation. So a lot of people actually use attention for interpreting your model for quite some time. And people still do with, even BERTs and, multimodal setting as well. So as I was saying, English, French, so it was developed for RNN-based encoder decoder model for English, French translation. And the idea is let's use hidden layers from all time steps to make predictions. So if you're familiar with the encoder decoder or sequence to sequence models, initially back in 2014, really back then, really 6 or 7 years ago, what people did was encode your input sentence to a single hidden layer, so fixed size vector. And then based on that, you would start decoding with another RNN. So you were assuming that all your input words would be accumulated or will be well represented by a single hidden layer at the last time step. But the neural attention is trying to address that kind of a strong assumption. So attention model. So as I was saying, let's use hidden layers from all time steps to make predictions. So when you are making a prediction based on a single, so this is, let's just forget about the decoder part. This is just the encoder part, because neural attention is has more emphasis on encoding rather than decoding. I mean, it is used while decoding, but the idea of using all hidden layer from all time step is the encoding part. So there's like, X1, X2, X9, all the way to X10, which are the inputs at individual time steps, and rather than using H10 for making a prediction. For example, in your project, the specs was that simply feed your chart events into a GRU and then use the last hidden layer, or to be more correct, hidden layer at the last time step to make the final prediction, the ICO, the mortality prediction. So you would simply take, for example, in here, H10, and then plug that into a sigmoid, logistic regression layer, and then make a binary prediction. But instead of doing that, let's try to use all hidden layers from all time steps rather than using the last one. And the way that you're using all hidden layer is actually doing a convex sum of them. So you have a alpha, you do a weight sum of alpha and the H's, and because it's a convex sum, you want your alphas to sum to 1. And the reason for using convex sum is you don't want your alphas to be arbitrarily large. You don't want them all to be large or all small or negative, to be precise. So because of this convexity, you are actually you're making your model more or less a bit more interpretable than intended. So right. So as I was saying, rather than using H10, you have now a context vector C, which is the weight sum between the alphas and the H's. And as I was saying, alphas must sum to 1. And then using those context vector now, which is actually explicit combination of the hidden layers of all time step. And then you take those C as now your representation vector, and then put that through a logistic regression layer. So if you've done that with your project 1, then maybe you could present, one of you can, maybe it would, first of all, it would have a better performance because because as I was saying, the maximum length of your input would be 100, or some people might actually be using 200 input sequence as well. So in that case, even with 100 sequence length, the H100 would probably forget a lot of stuff in the past. So, but if you used attention mechanism like this, then your performance would definitely increase first, and then you would get interpretability as a benefit, as an additional benefit. So if you had done that, maybe you could share your model with the class after the evaluation. All right, and then so attention, what is it good for? So it's not only good for improving the performance, as I was saying, but it actually C is an explicit combination of all past information. So alphas now you can use alphas to understand which input at which time step were especially more useful for making the prediction. So usefulness in this case, it's an NLP example. So usefulness from each word. So we can tell which word was used the most and the least to make the outcome. So in the translation case, we can, when predicting each, when decoding each word in an auto-regressive manner, you can understand which input words were most useful and least useful for predicting each, or for decoding each output words. And this is a bit more detailed, but the alpha weights are not given by humans. So obviously hopefully everybody knows this. So alpha weights are not given by humans. It's generated, or it's created by another neural network function, which are usually a single layer hidden, well, not single layer, usually a feed-forward neural network. So yeah, I will go into the details. So yeah, basically the attention generator function, MLP, is it receives as input the hidden layer itself, and then the output, which you want to output now, or the hidden layer of the decoder, actually. And then you would concatenate them and then put it through an MLP, and then try to figure out how important each hidden layer, each input step is, and then you get the scalar output. So you get the scalar output still. So there's no activation layer or anything. It's just a linear layer. So there's a scalar output, and then you take all the scalar outputs from all the time steps, and then you aggregate them using softmax functions, so that now the scalar outputs become a probability score. And then you have that alphas. Now, once you have that alphas, you can actually weight sum them with, you can use them to weight sum the hidden layers to derive the context vector. So that's the basic stuff. And then, yeah. As I was saying, for example, I'm not sure if it's English to French or French to English. Yeah, all right. Supposing that the original setup was English to French translation. Usually, isn't it the other way around? Yeah. Okay. So based on the heat map, it must be English to French. Okay. So setup was English to French. So this is the input sentence, and this sentence is to be encoded by the encoder RNN, and this sentence is to be decoded by the decoder RNN. And as I was saying, every single time you decode your output word, you determine the importance or the usefulness of your input words. So when predicting the word la, the first French word, you look at all the input words, and you can decide based on, because the input words will be convex summed by the attention function. So when decoding the first French word la, the most useful word or the highest attention was given to the word destruction. That's what this heat map means. And when predicting the French word destruction, or I guess it would be destruction or something like that. So when decoding the second French word destruction, the strongest attention was given to, again, the English word destruction, which makes sense because destruction is destruction. So again, this is a completely sensible thing. And then for here, for example, when predicting the French word, when decoding the French word equipment, the strongest attention was given to the English word equipment again. And interestingly, la series. So la, I think la is like the female form of the in French. So la Syria, and so the Syria, when decoding these two French words, the strongest attention was given to Syria and again to Syria. So it is working pretty well actually. And if you think about the diagonality of this heat map, the elements in this heat map is the diagonal elements. And if you think about the reason for that is because the word ordering between English and French is more or less the same. It's the SVO language, like there's subject and then there's a verb and then there's an object. But But if you try to draw this kind of heat map between English and Korean, then it would not be actually this diagonal, because the word orders are a bit different between Korean and English. So this diagonality actually indicates the similarity between the English sentence and French sentence. All right, so the question, okay, so question still remains. Is neural attention truly an explanation? So if you use attention mechanism somewhere in your model, can you truly say that it's an explanation? It's because people would say that it's an explanation. People would claim that it's an interpretable model, the attention model. People would claim that because it shows where the model pays attention to, where the model is attending to when creating an output, or when deriving a representation vector, whatever. If you use attention for something in your model, then you know which part or which input the model is attending to. So people would say that makes the model interpretable, or that makes the model explainable. But the attention strength does not equal correlation. So just because the attention, there's like a strong attention to some input, for example, here, for example, let's say that out of all the alphas, alpha 2 was like 0.9, and all the others were like 0.01 or something. So alpha being 0.9, so it's alpha being 0.9. That does not mean that H2 has a positive correlation with the output Y. Why is that? Can anybody answer? Why does attention strength not equal correlation? Yeah, we're almost reaching the end of the class, so maybe this could be the last topic that we talk about today. No minus, actually. That's a pretty good answer. Actually, please elaborate what you mean by no minus. Okay, a lot of different variety of questions. So no minus, actually, I'm gonna guess that means there is no negative attention. And answer from Kim Bo-min. Each hidden output contains the info of previous inputs. No, I mean, that's true. That's also true. So if you have multi-layered models, and each layer has its own attention, just like BERT or transformer, then that's also a correct answer. But the fundamental question was that if your model has only a single attention layer like this, and the alpha 2 is like 0.9, that does not mean that H2 or X2 has a positive correlation with the output. And so why would that be? It's not linear. I guess that's also partly acceptable answer. Like if this was a 10-point question, I would give that nonlinear thing maybe 5 points. All the attention, okay, so elaboration from Ryu Seung-woo, all the attention scores are positive, so it is not enough to say correlation. That is okay. That's also maybe like 5 or 6 point answer. That is technically true. But then again, you could actually twist your attention to allow negative attention. For example, you don't have to always use softmax. Actually, you can use 10H or whatever to allow negative attention. So, and then try to clip to restrict the range of the attention to be between 1 and -1. So in that case, I mean, it would no longer be a convex sum, but still it would be like you could still like try to represent or indicate that kind of indicates the strength of the input features. But the fundamental reason why attention strength does not equal correlation is because I guess Byung Young-jin kind of understood why. It's because there is another layer on top of. I guess maybe that's what Kim Bo-min meant. So because there's another layer on top of the C context vector that converts it to the output Y. So this is not the end of the prediction. There's another prediction layer. At least there's always a linear prediction layer somewhere, and that combines the output, that kind of twists the attention strength to either positive or negative strength. So even if your alpha 2 was like the highest, like even if your alpha 2 was 0.9, it would eventually, it could have a negative, like 90% negative impact to the output because of the WO here, or it could actually have a positive 90% impact to the output because of the WO here. It depends on what WO is doing here. The linear prediction layer's weights, they make everything different. So that's why attention strength does not equal correlation. So you can't, you have to always be careful. Just because, for example, here, just because like Syria here was most heavily used for predicting law, it does not guarantee that it had a positive correlation. I mean, obviously here it's positive correlation, but it does not always guarantee, technically, mathematically, it doesn't guarantee positive correlation or negative correlation for that matter. You have to actually understand what's going on after the context vector or after the attention layer. So I guess if you combine all the answers from Kim Bo-min, Byun Young-jin, and Ryu Sung-woo, I guess that makes a perfect answer. And again, ultimately, even if you can actually make your model, even if you can make your attention kind of like a correlation weight, like, I mean, so after this, we're gonna study retain, which is the which is a model here that we're going to talk about. This actually makes the model a bit different so that the attention strength exactly equals correlation. So that is the contribution of the model. But ultimately, is correlation enough? Just because even if you modify your model so that your attention strength equals correlation, does that mean your model is completely interpretable? Which equals to asking, if you can understand the correlation between a feature and the output, can you say that your model is interpretable? Because some people say the correlation is not enough. Like, it must be causal. So correlation is not causal. So your model has to be causal in order to actually understand what's going on. Because correlation can be misleading always. So that's another. I mean, we're not going to deal with that, like causality and correlation, that kind of like high level technical details in this class, but still it's a thing to think about. All right, we have it's 47. All right, I guess, yeah, just maybe a few more minutes on recapping recapping with what people usually do with longitudinal EHR. So we've already seen this a lot of times. So a patient, so far in our example, we only took a look at the RNN model, which gets single input at a time, single feature input at a time. For example, in your ICU mortality prediction project, you inputted only one feature at a time. Supposing that all your item IDs were, they occurred at different timestamps, you would feed one item ID at a time. So that was more or less the setup for now, and which was also the setup for readmission prediction. I mean, ICU readmission prediction, hospital readmission prediction. But if you think about but we've briefly covered this kind of architecture, this kind of like diagram for a few minutes. If you think about the outpatient setting, outpatient being the 외래 환자, if you think about the outpatient setting, the patient visits the hospital multiple times over few years, and single visit is a one-shot thing. You don't get admitted, and you don't sleep in the hospital. You go to the hospital, get diagnosed, get treatments or get prescription, and then you leave. And that all happens within 10 or 15 minutes because doctors are busy people. And so that you can think of individual outpatient visits as a set of medical codes. For example, here, these two codes are diagnosis codes. This is medication code. This is a procedure code. And again, maybe a few years later, or maybe a few months later, you visit hospital again because of cough and chill. and then maybe a few days or a few months or whatever. Like the time gaps are irregular, obviously, because you don't visit hospital in a regular interval. So maybe a few months or a few years after the second visit, you make a third visit to the hospital, and then this time you have fever and you get prescribed with Tylenol, and then you just take an X-ray as just a precaution, something like that. So that this would be a typical outpatient record. And when you think about putting this into the model, you no longer can put one feature at a time because multiple features happen at each visit. So in that case, you would have a multi-hot vector. So for example, let's say that there are 40,000 unique medical codes. The 40,000 thing is what we always use, because there are roughly 10,000 diagnosis codes, 20,000 medication codes, and 10,000 procedure codes, more or less. So we're going to stick to the 40,000 example most of the time. So you would prepare a 40,000 dimensional zero vector, and then you would tick the one that corresponds to the features here that occurred at each visit and tick them to 1. And of course, all the others will be 0. So it would be extremely, extremely super sparse vector. And then you simply embed this to a lower dimensional space. So a simple embedding, you could actually transform, you could have like a nonlinear vector activation function here, but if you don't want to, you don't have to. It's up to the designers, because the upper layers would be highly nonlinear anyway. So here we are using a nonlinear activation function. So basically, I'm pretty sure we've already talked about this. If you have this, if you multiply this vector with this embedding matrix, this is the same as converting this to an embedding, converting this to an embedding, this to an embedding, this to an embedding, and then summing them up. That's what's happening in this embedding layer. And you don't simply sum them up, you put them through a nonlinear activation function as well. But summing them up is the core, is the essence of that operation. And then that becomes your visit vector now, because you've summed them all up. So this is a visit vector, and then you put visit vector into your RNN, and that becomes your first hidden layer. And then you do this for the next visit, next visit, next visit, and then until the next visit, you put multiple codes at a time, at each time step, and then you get HT, which is essentially now a patient representation vector, because patient makes multiple visits. So if you aggregate multiple hospital visits, then that is now a patient level thing. So HT is now a patient representation vector. And then you put this through a logistic regression function to predict something, whether the patient would develop a certain disease in the future, or if the patient will die in the future, something like that. So that's how you do a patient level prediction. In this case, I guess we are going to use heart failure prediction, but it doesn't have to be heart failure. It could be any prediction. So that's the setup. And then we're going to make this into a completely interpretable, when we're going to talk about what I mean by completely interpretable. Well, we're going to look at a completely interpretable model based on this setup. So that will be next class. All right. Any question for today? Yeah, more or less, we looked at the high level concept, the philosophy of the interpretable models, and a couple of examples. But starting next, this Thursday, we'll look at a bit more technical stuff. All right, if there are no questions, I'll see you guys this Thursday. Bye-bye.